All right, Calculus 2. Today we're going to be talking about the area between the curves. And so as you can see here in chapter 6.1, we have two curves. We've got this blue curve up on the top and a red curve here in the bottom. And we are going to call this blue curve y equals f of x, right? And then we're going to call this bottom curve here y equals g of x. And so we are interested again in the area between the curves. And so any small bit like we see right there, if we were to break this into partitions, right, we're going to be adding this top part to our area. But note for this part down here, we're going to be subtracting that area because it's a negative area. So whenever it's underneath like this and the area is negative, again, we're interested in the area, not the integral. And that is a very important distinction, right? An integral has magnitude and direction. However, when we're talking about area, it's just magnitude. So we can't have a negative area of something. And note that if we're subtracting out this amount, right, it becomes negative, as I said. But over here, right, that area would be positive. And if we take the integral all the way up to the blue line, the f of x line, right, it would be this entire rectangle, but we would need to subtract out this bottom part. So regardless of whether the red is below the axis or above the axis, you still subtract. So when we calculate the area, we're going to say take a limit as n goes to infinity. Remember, n stands for the number of partitions we are breaking this area up into. And this will be over the integral from j equals 1 partition up to the nth partition of f of x evaluated somewhere inside of j minus g of xj, again, where xj is evaluated somewhere in the jth partition. And you got to multiply this by delta x. Right, where delta x is the width at xj, right? This would be our jth partition. So note that this f minus g, that is the height of our rectangle. Or should I say the height evaluated at j. And that would be the height evaluated at that j right there, right? Different j. So we're good. And so we're again delta x is b minus a divided by n. Note that we're taking the limit as n approaches infinity. So when we take this limit, it becomes an infinitesimal, right? Because b minus a, that's a finite length. And so ultimately this will become the integral. And b can be anywhere. We'll just put an a here and a b there. So the integral from a to b of f of x minus g of x times dx, right? Our infinitesimal. So we see all the analogies. We see this typed up a little bit more neatly right here. Now there's a very important caveat, very, very important caveat you guys have to keep in mind. And that caveat is this. for this to work, f must be greater than g for the entirety of the interval from a to b. We will deal for when this is not the case, but for right now, for the interval we're working with, f has got to be greater than g for this to be true. Again, we will look at cases where this is not true, where they change, but that will be for later. All right, so to this next problem, we have two lines. We've got y equals x, and we have y equals x minus 1 squared minus 1. And we are going from the interval from x equals 0 to 3. So let's go ahead and graph our lines. Again, we know that we're just going from 0 to 3, so let's just make a note of that there. And so the line y equals x, well, that's simple enough. It's a straight line with a slope of 1. There we are, y equals x. Now note this one, the second line, note that that is a parabola with a vertex at +1 and -1. So we know the vertex is down here of this parabola. The parabola opens up and is not stretched. So it goes right 1, up 1, left 1, up 1, right 2, up 4. And note that puts us right there at the intersection point with y equals x. Right, and then left 1, up 1. And of course, left 2, up 4. And so the area of interest is this area right here. With intersection points at 3, 3 and 0, 0. Okay. So we just set this up with the integral of f of x which is our top guy, minus the bottom guy, dx. And again, this equals the area. Okay. And ignore that mark right there. It's just, I'll hide it. There we go. Never happened. All right, so let's start working this. Getting the integral from 0, 3 of x minus good. So I see already we've got a 1 minus 1. And we have an x minus a 2 of x. So those two terms are going to combine. So giving us negative x squared minus 2x makes that a positive 2x. So all right. And now we take the integral And note we do not write plus c, right? Because this is a definite integral. You only do plus c if you're dealing with a indefinite integral. Okay. And so we have negative 1/3 times 3 to the 3rd power plus 3 times 3 squared divided by 2. And of course, the second one is simply minus 0. Okay. All right, I'm going to carry this over here so we have a little more space. So we've got negative 3 squared plus 3 cubed over 2. And now it's just a simple workout problem. Right? We've got negative 9 plus 27 over 2. Okay. So negative 18 over 2 plus 27 over 2 will give us 9 divided by 2. Good. Okay. All right, so for the next example on the page, it asks you to do a MATLAB exercise. We're going to do that in class together. So I'm not going to do that right now, but we will look that over in class. But we will be doing this one right here. So note that we have y equals x minus 1, and y equals the natural log of x. So this is just the identity equation shifted down 1, or a straight line, the slope of 1, and a y-intercept of negative 1. However you like to think about it. Regardless, here's the straight line. Regardless. There we go. And then we have y equals the natural log of x. Again, it is very important that you guys have the shape of this graph down. It is going to be coming up multiple times. So natural log, right, it goes through here, and it goes up and away like that, very slowly, of course, and then comes down like so. Okay, and don't forget we also have this other line, y equals negative 1. And there it is. There is our area. That we are interested in. Okay, so we know we've got a coordinate here at 1, 0. Clearly we've got one here at 0, negative 1. And let's figure out this coordinate right here. Note this is on the line y equals natural log of x, and we want to know when does the x, right? We already know the y line, it's -1, but we want to know the x value, so we set it equal to -1 times the, or equals the natural log of x. So note that this is the same thing as saying e raised to the -1 must equal x. Right, that is our value right here. So 1 over e. So we've got the coordinates of all of the vertices of this area. Now, if I go from the area from here like this, it works fine from here to here, but note that afterwards it starts getting a little tricky. I got some tricky geometry I got to worry about. So instead of doing that, we're going to go this way. So that way I don't have to switch my integral partway through to account for this extra thing here. So that's going to involve, instead of saying dx, dy, and we're going to have to put everything in terms of x. So our area is going to go from the integral from -1 to 0. Note I don't have to worry about the 1 over e when I go this direction because I'm only looking at the y values. And so this line right here, this y, right, that's actually what I want to show you, right, this is equivalent to saying e raised to the y equals x. And so this becomes e to the y minus, and again we got y equals x minus 1. We got to rewrite that one. To x equals y plus 1. Okay. So to take the integral, of course, this is ey minus y squared over 2 minus y, and we're going from y equals -1 to y equals 0. So a lot of these go away, but note not all of them go away when y is 0. Okay, just plugging the numbers in. E to the 0, of course, is not 0. It's 1. The rest of these, of course, are just 0. So 1 minus 0 minus 0. And then over here, we've got 1 over e minus a half plus 1. So now I got 1 minus 1. Leaving 1/2 minus 1 over e. Okay. So again, we did this with dy. We can also do this with dx.